Hi, welcome to another lecture on Calculus 2. We are going to talk about lines and planes in three dimension. Let's go and take a look at this interesting topic. So, we're planning to give a description of lines in 3D, a description of planes, and how to sketch planes and find the distance between these items, points, lines, and planes. Let's start with the simplest. How would we give the equation of a line? Well, this is something that you have seen in college algebra, algebra 1, 2, many different places. We are doing essentially the same thing in higher dimension. And the description actually we are going to give right now is simpler than what you had seen before. Let's see how we describe a line in space. So we have a three-dimensional setting. We want to describe a line in this space. We want to give a relationship between the coordinates x, y, z for the points on the plane. Most traditional way of handling this issue is to give location of a certain starting point on the line. Like start at some point, let's call this point R0. So for example, starting point can have coordinates x0, y0, z0. And then starting from this point, we want to specify all the other points. Let's call this general point on this line, let's call it point R. Very significant descriptor of a line is a vector that is parallel to it. This vector, let's show it by V. This is a vector that is parallel to the line, sometimes referred to as a direction vector or guiding vector, or description like that, direction vector. So what's the role of this? The role of direction vector is the following. Suppose we want to arrive at the location R. What do? We can go to, from the origin, we can go to our starting point, and then from here take certain number of steps. Each step would be a copy of this direction vector. So I could go perhaps 1v, and maybe by the time I make my second step, perhaps I have arrived at the location that I want to be. Perhaps I need to take 3 steps or 4 steps, maybe 5.5 steps, and so on. So to arrive at R, we say the recipe is from origin go to starting point R0 and take so many steps of V. The number of steps, we are going to show it by the letter T. That's going to be our parameter, number of steps we make. For example, here it looks like I'm taking 2 steps. Number of steps times V. So T times V in this shape 2V has taken me from R0 to R. So R is given as a starting point R0 plus certain number of multiples of V. So this is referred to as the vector form of the equation of the line. That's it. You notice that the formula is very simple, clean, and it covers all the cases that you have seen in college algebra and such. Now, if you want to worry about, well, what happened to my x, y, z? Well, go ahead and for R write x, y, z, x, y, and z. Well, R0 was our starting point, some x0, y0, and z0. T is a parameter that specifies different points on this line. V can be given as a vector, so that's going to be A, B, C, perhaps some 3 numbers. So here I'll be multiplying with A and B and C. That's my vector. So if we want to take this equation, open it up, so this is one form. This is a copy of that with the vectors written as triples. Now I can say the first one is equal to the first one of this plus the first one of that. So I can say x is x0 plus t times a, or a times t, and y is y0 plus b times t, and z is z0 and plus c times t. This three equation actually sometimes is referred to as the parametric form. And then sometimes we want to mention the line without mentioning anything about the parameter. So I can calculate t from each of these three equations and say, well, it's the same parameter, so that all of these things have to be equal. So I say x minus, so let's say, suppose I want to calculate t. From the first one, I can say x minus x0 divided by a, assuming that a is not 0. I can do this. So x minus x0 divided by a, or y minus, do the same thing on the second equation, y minus y0 divided by b, or z minus z0 divided by c. And in that case, typically they drop the letter t. I mean, it's up to you if you want to drop it or not, and that's called the symmetric form. So symmetric form of this equation is given like that. So this the portion that has a t in it, sometimes it's not written out, but the common value of all these three is that. So that we notice that this is a very simple clean-cut description of what the line is going to be. Here, let's go ahead and practice it in a simple example. Find equation of line through point, let's make our numbers 1, 2, 3, and parallel. So this point is playing the role of the starting point, and the parallel to, well, now we give the direction vector. Let's make it 4, 5, and 6, just to remember. So general equation is just r plus r0 plus tv. Now, depending on how you want to write it, suppose I want to write the parametric form of it, so it's going to be x equal to x0, 1 plus 4t, y is going to be y0, which is 2 plus 5t, and z is going to be z0, which is 3 plus 6t. So if I want the, remember we call this thing parametric style. Now if I want to, in the so-called symmetric form, so it's going to be x, we calculate t from all of these equations, x minus 1 over 4, or y minus 2 over 5, or z minus 3 over 6. That's going to be the symmetric. And the common value of all of these three fractions is just the parameter t itself. So now you can apply this general idea to a variety of problems that you're going to see in your homework, and these are all pretty much similar to each other. Next up, how about describing a plane? What is the simplest way of describing planes? Of course, for describing plane. We have to be in 3D. It doesn't become an interesting problem. You're just in 2D. The only plane you have is just a XY plane anyway. But now in 3D, we want to give description of a plane. So suppose here I have a plane sitting in space. Again, there are many different ways of specifying a plane, and you're going to see a variety of them in the homework problems. The standard way of describing a plane is through its normal. So a plane always has a normal. So here I draw a normal. We notice immediately we could have come out or gone inside to the other side. There's essentially two choices of normals. One is essentially negative of the other one. Now, how does a vector, so this is the normal vector. Normal means perpendicular. Normal vector, how does that describe a plane? Well, again, just like what we had with the story of a line, we needed to specify some starting point on it. For plane, same story. We go and specify some point on this plane. Let's again call it R0, x0, y0, y0, some location on plane that we know for sure is on the plane. Now what? Now what do you think is the relationship between this line, this green line, and that blue line? Well, we said this is perpendicular or normal vector to the plane, which means it's perpendicular to every line on that plane. This is a 90-degree angle. Well, not only that, but if I draw any other line through R0, these two are perpendicular to each other. In what sense? In the sense that if I take this vector n and transport it parallel to itself until it comes and touches this other green vector, these are perpendicular to each other as well. So this normal is normal to every line, regardless of what line I draw here. They all have the same property, that it is perpendicular to all lines on the plane. So try to visualize this thing for yourself. Just hold the pencil perpendicular to your notebook and put another pencil on the notebook and visualize the angle between the two of them. Convince yourself that it makes sense to say this standing pen is perpendicular to that other pen that's lying down. Okay, so if it is so, then what? Well, let's go pick one of these things. Let's just color it so that stands out. Maybe I color it gray here. Okay, so I take this vector. Okay, pick a point on this, and let's call this point R, just like above. What do we know? We know that the vector that goes from R0 to R, this thick gray vector here, is perpendicular to n, because n is perpendicular to every vector on this page. Anyone that you pick up, this one is going to be perpendicular. Well, what did you learn about perpendicular vectors? What is the telltale signs of two vectors being perpendicular to each other? Of course, we learned in the previous section that the dot of them, if I dot these two vectors, I get 0. Well, that's exactly the equation we are after. So that is the vector equation of a plane. That's actually what we were after is right here. But if we are more accustomed to x, y, z's and so on, we do the following. First of all, this Let's go back to our familiar stable. Okay, x, y, 0, y, 0, z, 0. This point, let's call it x, y, z. So this is representative of any point on this plane. Now r0 to r, the vector r0r, is obtained by just subtracting these two. That is, how do you go from x0 to x? Well, you have to travel x minus x0. How do you go from y0 to y? Well, y minus y0, and the other one z minus z0. Okay, so this is the description of this thick vector here. How about n? N as a normal vector is going to be given to us as three numbers. Let me just specify it, for example a, b, c, or something like that. So n times that means a, b, c, the vector a, b, c, dotted with the vector x minus x0, excuse me, let's correct this thing, x minus x0, y minus y0, z minus z0. That is, all has to be 0. Well, how did we dot two vectors? First with first, second with second, third with third, and add them up. So a times x minus x0, b times y minus y0, and c times z minus z0. That has to be equal to 0. Now sometimes we want to clean this up. X, y, z are the variables, so I separate them ax plus by plus cz, and the rest of them are constants, ax0, by0, cz0, and they're all being subtracted. So maybe I pile them all, ax0 plus by0, cz0. No, all of these constants might be combined into a single name. Let's call them d or minus d or whatever you like, and that would become the equation of the plane. Okay, so sometimes they write the equation of a plane as ax plus by plus cz. Maybe they keep this number on this side, maybe they take it to the other side of the equation. Different books have different styles themselves, and this is called the general equation of a plane. Notice this is a single equation, unlike what we had in this situation where you either have three equations like this or a set of equations like that, and so on. For the case of a plane, it's just one equation. Let's go ahead and practice. Find equation of a plane. So this is like a simple example. In the homeworks you're going to be asked some variations of this. You have to think a little bit about extracting what you need. Extracting what you need, typically that means find a point that the plane goes through. So again, let's suppose this is the plane goes through 1, 2, 3, and normal to the vector. So now this is a normal vector, so let's call it maybe 4, 5, 6. So what do we write? So x minus 1, y minus 2, z minus 3. This dotted with 4, 5, 6 has to be 0. So this is the normal vector, and this is the displacement from base point to some arbitrary point on the plane. The dot of these two has to be 0. So we write first component times x minus 1, second 5 times y minus 2, third 6 times z minus 3 is equal to 0. That's the equation. Now if you want to clean it up, x, y, z traditionally piled up together, minus 4, minus 10, minus 18. So we might as well clean this up. 4x plus 5y plus 6z, 14 and 18 looks like it's minus 32. Okay, so that would be the general form. Again, in some texts they prefer to put this number to the other side. That's a matter of cosmetics. It's all the same. Now, how about other styles of describing a plane? Well, what else could there be? Sometimes you see that you are interested in some vector. Let's call this one maybe a vector u, and there's another vector here, say vector v, and then you're asked to consider a plane that passes through some point. Let's call that point again r0, and has some vectors parallel to u and some vectors parallel to v. So I could just copy u and v here. So I draw vectors parallel to u and v starting at r0. And what does that give me? Well, first of all, you notice that you want to make a plane out of it. Best visualization for that is a parallelogram that is built on top of u and v starting at some point r0. Okay, so now you can take this parallelogram and extend it in space. The plane of that parallelogram is going to be the plane that we are after. If you want to make it nicer, you can make another of these diamonds and another one of these diamonds here and another one here, and so on. You can continue building it like this. That is going to be like tiles placed next to each other in space, and you can make your plane out of these. Well, I had to spend a bit more time to draw this thing accurately, but gives you an idea how to arrive at a particular point on this plane. Suppose I want to arrive here. How would I give an address to this location? I say, well, start at r0, then take 1, 2, 3 steps in direction of u, and then take 1 plus 2 steps in direction of v. So how do I get to this point? I can say start at r0 and take 3 steps of u and 2 steps of v, and I arrive at this location. Well, how about here? Well, I get 3 u's and 3 v's. How about here? Well, just 3 v's will do it. How about here? Well, take 1 u and 2 v. So I can arrive at the location by going from r0, take so many steps. So many steps? Let's call it t steps in direction of u, and the other one is a different multiple. Let's call that s steps in direction of v. So that would be actually our parametric description of a plane, similar to what we had for the line. So if I want to arrive at the location r, specify starting location, and then specify 2 direction vectors. Let's call one of them u, and then you take so many steps in direction of that, and so many steps in direction of v. So s and v becomes your parameters. So this is parametric equation of a plane. In general, this is quite more common because people are used to XYZs all the time, but a description that is kind of neater and cleaner is this one. This is the parametric equation of a plane. Well, how do you go from one of these forms to the other one if you have this information given to you? How do you go back to this information? Well, for here what was so significant was this normal vector n. If I have my normal vector, then I say I apply this idea, and then I'm all done. So how do you go between the two of these formulation? Well, if you have a vector u and a vector v, how do you find a vector that is perpendicular to both of them? And one of the sections that we had a couple of lectures ago, let me see. So our idea was that we show this picture and you think, time to pause and think for yourself. Given the question now is given two vectors, how do you find the third one that is perpendicular to both of them? Okay, this was a lecture we had just a couple of days ago. So of course, if you cross multiply u and v, you get a vector that's perpendicular to both of them. So if you want to go from one of these descriptions to the other one, you can take u and v, cross multiply them, and then you get your n. And once you have your n, then you can do what we did here. So you might play with that idea in some of the homeworks that you have. Another nice application of ideas that we have developed so far is how to find the angle between two planes. Well, very simple. So let's go back to what an angle is. In the angle, well, you have two lines, yeah. Well, you're talking about the angle, either the acute one or the obtuse one. To specify which one you mean, pretty much all of these problems push you for the acute angle between the two shapes that you have in mind. Okay, so again, what was the tool that we had for finding angle between two things? So we said, again, lecture we had a couple of lectures before this one, that if you have a line, let me draw the other one, and the other one, to describe the angle between the two of them, you can consider normal to both of these things. So I consider normal to the red one and the normal to the blue one, and the angle between the original shapes is same as the angle between the normals to themselves. Well, the same idea applies to the planes. If you have two planes, like if I have a plane number 1 and a plane number 2, and I want to find out what's the angle between the two of them, what makes sense to do, let's again go ahead and color it maybe in the same style that we had. So say the red plane here and the blue plane here. So the red one has a normal and the blue one has its normal, and instead of going after this angle, we can go after that one. Well, so what we need to do is to find the normal for plane 1, normal to plane 2, and then what we have is that the cosine of the angle, let's call this theta, theta is going to be what we saw from the formula we had before, n1 dotted with n2 divided by norm of n1 times the norm of n2. And in this formula there is still room for either getting the acute angle or the obtuse angle. If you want to aim for the acute angle, make it positive, and then you are all set. So if you want to have the acute angle, don't forget, take the absolute value of the item in the numerator, and that gives you the angle between two planes. So again, the details I'm going to leave it to you. For the example, in the homework, you extract the normals. How do you extract the normals? Well, if a plane given to you, how do you get the normal of it? Well, the normal, you take multiples of x, y, z, a, b, c. That is exactly the normal that you want. So if you want to get the normal to a plane, it's just multiples of x, y, z that gives you the normal, and then you dot the two of them, and that is going to set you on the path to calculate the angle between the two vectors. Sometimes questions ask you about finding the line of intersection. This is the line of intersection. Looks like a hinge, and this will be the door. So this is the line of intersection. How do we find that? Well, you take the red plane. Suppose the red plane has the equation a, let's call it a1x plus b1y plus c1z plus say d1 equal to 0. And that blue plane is also given to you. Suppose that has quite sure what that is. Okay, the blue plane has its equation. Let's call it a2x plus b2y plus c2z and say d2. If you want a line of the intersection, it means you are going to consider this xyz here and xyz to be the same. XYZ meaning the points that are common to the two planes. So the two equations are going to be parts of a system of equations. So if you want to find the line of intersection, you solve the set of equations where each equation is one of the planes that you have. Okay, how do you solve an equation like this? Let's go ahead and practice. Suppose I have the following problem. Find the line of intersection of two planes. Maybe I pick up an example from your text so that here's a problem 65. 3x plus 2y minus z is equal to 7. This is one of the homework exercises. The other one is x minus 4y plus 2z. Let me modify that a bit so that it becomes a bit more general. Okay. When you look at this equation, something might be a little bit unsettling for you, especially if you haven't taken your linear algebra class, because it isn't that we are looking for a number for x, y, z. Rather, we are looking for a parametric description of this. You are more accustomed to set of equations where the number of equations is same as the number of variables. If I have x, y, z, I have 3 variables. I expect to have 3 equations. Well, I have only 2. What does that mean? It means typically you have infinitely many answers for this type of an equation. You have to describe it parametrically. How do you do that? So one way to do this thing is take one of these 3 variables, take it to the other side, so it becomes 3x plus 2y is equal to 7 plus z, and then the other one is x minus 4y, and that is 1 minus 2z. Let's make sure my z's don't look like a 2. Okay, now I can go ahead and find x and y in terms of z. So x is going to be some expression in terms of z, y is going to be some other expression in terms of z, and then z is going to be the parameter for my line. You remember when we described the lines at the beginning, the lines had some parameter. Now that parameter could be any of these three variables themselves. So this is one situation where this happens. Well, how do you solve this one? Easily. For example, if I double this equation and add to this, so if I double that, add to this one, I eliminate y. Or if I triple this equation, subtract from that, I would have eliminated x. So eliminate either x or y and you are on your way. So I double this and add to this, double of this and add to that, becomes 7x. 4 and 4 cancel, and then 14 and 1 becomes 15, and my z's accidentally have cancelled too, so my x is 15/7. Okay, if I take this thing and then plug it back in my either of equations, so for example I take it, put it here, and then I'll have 15/7 minus 4y is equal to 1 minus 2z. So y becomes, let's write minus 4y is 1 minus 2z minus 15/7. I divide by minus 4, so I'll get y is equal to minus 1/4 plus this divided by 4 becomes 1/2 z, and this pi divided by 4 becomes 15/28. So this is my y. So let's write our x turned out not to have any z's in it. Our y, let's clean this up. So I'll have 1/2 of z. Let's put this thing into a common denominator. I have 28, and then I have minus 7 and plus 15. Let's clean up as much as we can. 1/2 of z, and then this is 8/28. So perhaps 1/2 of z, divide this by 4, so I'll have 2/7. So 2/7 plus 1/2 of z. How about z itself? Well, z is our parameter. Z is just equal to z. How is that a parametric equation of the line we are after? It's customary to just uses t on the right hand side so that it looks like the kind of equations we had before. 15/7 y is equal to 2/7 plus 1/2 of t and z is equal to just t. So this is the parametric equation of the intersection. Now in this problem, it so happened that there is no t here. What does that mean? It means x is a constant, and therefore your line is has a fixed x at all the time, and that makes the line to be parallel to the YZ plane. Okay, if x is a constant, it means your line is parallel to the YZ plane. So we practiced this concept as well. Now how about sketching? Let's talk about sketch as well. Sketch of a plane. Suppose we ask you to draw something, say 2x plus 3y plus 4z equals to, say, let's make the problem easy, say 12. Well, you remember from your college algebra and other classes, to draw a line in xy plane, you needed a point and a slope, and then you go ahead after that. That's one style. Of course, another style was to get two intercepts and then draw that one. Sometimes that idea is more practical in 3 dimensions. So in 3 dimensions, suppose we are after this plane, and the job that ahead of us is substantially more complicated than before because of the high dimension we are living in. So one idea to go after is the idea of intercepts, just like in college algebra. Intercepts, well, situation is more crowded. We have x-intercepts, y-intercepts, and z-intercepts. Suppose I want to find the x-intercept. That is, I'm right on this line. The question is, where would I be? Well, if I'm on this line, my y and z are 0. If my y and z are 0, so I have 2x plus 3 times 0 plus 4 times 0 is equal to 12. So of course my x has to be 6. So I say 1, 2, 3, 4, 5, 6. So I choose my units and then go accordingly. So that's the x-intercept. Same idea with the y-intercept. The y-intercept, who's going to be 0? Of course, x and z is going to be 0, and my y turns out to be 4. So it's 1, 2, 3, 4. So that is my y-intercept. Same story. Z-intercept, x and y are 0. Z has to be 3. 1, 2, 3. This is 3. This is z-intercept. So whatever that plane is, when it cuts the coordinates, it leaves these 3 points. Well, if I connect these 3 points, I have a good idea where that plane is sitting. That plane is an extension of this triangle. So I visualize this triangle, of course, extending on this direction, this direction, this direction, and that makes my plane. So that the sketch of that is obtained this way. So we have the idea of intercepts. We also have another new idea, which is to use the concept of a trace. Trace is the intersection of our plane with any of the coordinate planes. So for example, this is a trace. If I have that one drawn, I can say that I know where the plane is. So this plane has three traces. You have one trace per each of these coordinate plane, and then you can draw them, and then have an idea of where your plane is. So for example, where is this yellow line? Well, the yellow line is on the xy coordinate plane. Xy coordinate plane, well, on xy coordinate plane, z is 0. So if I replace z by 0, I get in the equation of this yellow one, that is 2x plus 3y equal to 12. 2x plus 3y equal to 12 has x-intercept and the y-intercept. I draw it. However, I would have drawn it back in high school in college algebra, and this is just a copy of that. So that is the equation of this trace, and I can do that for any of them. For this one, who is it that's going to be 0 on this blue line? Of course, I'm on the xz plane, and y is going to be 0, and what's left there is just 2x plus 4z equals to 12. That is the equation of this one. And similarly, if you're down here on yz plane, your x is 0, so your equation is going to be 3y plus 4z is equal to 12, and that is the so you can get an idea about the plane by drawing these. Okay, so we talked quite a bit about various things we can do with the lines and planes. We talk about lines, planes, sketching them. Let's keep this thing for a separate short lecture. And so until next time, good luck and God bless.